Then we move on to preparing data for modeling. So we imported time delta from data time. So sales df is equal to feature df dot replace np infinity, negative np infinity, and np nan. Basically, this replaces like the infinity and negative infinity of nan before like dropping the nan values itself. Then we have model df is equal to save df dot drop na reset index drop equals to true. Basically, it just removes the rows with like nan values. Then we have target is equal to total sales all the way till feature columns is for column for call for column in model. You have columns if column not in date. Target total quantity, total profit or order count. Basically, this sets like the predictive target of total sales and creates like a list of column features. And then we move on to printing the model shapes, the number of features in the model, and the date range for modeling. Then we have split data equal model df brackets data dot max minus delta time delta of 30 days, all the way down to test data, which is equal to model df brackets model df dot date greater than split data. Basically, what this block of code does is basically splits the data into training and testing sets based on the time, using like the last 30 days as like the test set. Then we move on to printing the training set, the testing set, the training period, and the testing period. Then afterwards, we do xtrain is equal to train data, feature columns all the way down to y test is equal to test data brackets target. Basically, this extracts the feature matrix from like the xtrain, xtest, and target vectors of like ytrain and ytest for like model training and evaluation. Then we print out the feature matrix shape by using xtrain.shape and xtest.shape. Here we have the modeling train here. So here's the output. So model data set shape is equal to 553 rows, 56 columns, number of features 51. Date range for modeling is from February 16, 2014, all the way down to December 29, 2017. Training set has 530 samples. Test set has 23 samples. Training period is from February 16 all the way to 2014, and till November of 29, 2017. And the test period is from December 1st, 2017, all the way down to December 29th of 2017. And the feature matrix shape is for training is like 530 rows and 51 columns. Testing is 23 rows and 51 columns. Next, we move on to model training and evaluation. From sklearn.linear model, I imported linear regression. From sklearn.ensemble, I imported random forest regression and gradient boosting regressor. And from sklearn.metrics, I imported mean absolute error, mean squared error, and R squared. So models is equal to linear regression with its parameters, random forest with its parameters, and gradient boosting with its parameters. Basically just defines a model for the training. Then we have results is equal to empty brackets. Basically this is as a way to store all the results for each of the models. Then we have for name model in model items, print training name. Basically this loops through each of the model and prints out what models are basically being trained. Then we have model.fit, xtrain, and ytrain. Basically this fits the model to the training data. Then we have yPredict train is equal to model.predict xtrain, and yPredict test is equal to model.predict xtest. Basically this makes predictions both on the training and testing sets. Then afterwards we calculate the metrics for the mean absolute error for the training and testing set, the mean squared error for the training and testing set, and the R squared for the training and testing set. And afterwards we store the model, the metrics, and the predictions in the results dictionary over here. Then afterwards we print out each of the metrics for the training mean absolute error, the testing mean absolute error, the training mean squared error, the testing mean squared error, and the training R squared and the training R squared. So here's our outputs for this. So training linear regression with its metrics over here for mean absolute error, mean squared error, and R squared, and the same thing for the testing side. Here we have the one for the random forest with its mean absolute error, mean squared error, and R squared for the training and the testing side, and the same thing for the gradient boosting for the training and testing side. Next, we move on to comparing models. So if len results is equal to 0, print no models are trained, else compare df is pd.data frame with the parameters of model, test mean absolute error, mean squared error, and test R squared, and then comparison df.round3. So this block of code basically does it what it basically lists each of the model and its training and its key test metrics, and it prints the data frame and rounding the metrics to to the third decimal place. So here's our output over here. The models, the linear regression, random forest, gradient boosting, training set for the training for the testing mean absolute error we have of 975, 960 for linear regression, 964 for random forest, 959 for gradient boosting. For the mean squared error for linear regression we have 1208, 1212 for random forest, and 1167 for gradient boosting. And for r squared, we have 0.03 for linear regression, 0.057 for random forest, and 0.1125 for gradient boosting. Basically, what this data tells us is that all the models have a very high error values for the mean absolute error and the mean squared error, meaning that the predictions now were not very close to the actual sales, and the R values are low, so from and the R values for each of the models are pretty low, basically it's explaining that only a small fraction of the actual sales variance. Overall, the gradient boosting is the best, as it has the lower errors but and a higher R squared, but overall none of the models have a highly accurate, or none of the models are highly accurate. Next, we move on to feature important analysis. So fig axis is equal to plt.subplots 1, 2, 3. Fig size is equal to 20 to 10. Basically, this creates a figure with 3 horizontal subplots for visualizing the feature importance for the 3 models. So here we have the random forest feature importance. So RF model is equal to results random forest brackets models all the way down to axis brackets 0 dot set x labels importance. Basically, what this block of code does, it gets the trained random forest model, and it basically extracts the feature importance and creates a data frame, and basically sorts and selects the top 20 most important features, and then it basically plots a horizontal bar chart for these features. And it's the same thing for the gradient boosting feature over here. Basically, we get the trained gradient boosting model, extract the important features, sort them, and then select the first 20. Then we move on to linear regression coefficients. Basically, a linear model is equal to results on linear regression brackets model all the way down to axis brackets 2 set x label coefficient. Basically, this block of code gets to the trained linear regression model and takes the absolute value of the coefficients and sorts them, and basically selects the top 20 and plots them in the third subplot. So here's our visualization for this. So for random forest, the top feature importance is the total sales lag 14 all the way down till sales acceleration. And for gradient boosting, the top feature importance is total sales lag 14 all the way down to sales acceleration. And then for linear regression, for importance coefficient, we have the month all the way down till day of the week. So yeah. So this was the entire project. Thank you for listening and watching.